It's my pleasure to introduce you to you today, Satoshi Masoka, who is a global scientific information and computing professor at the Tokyo Institute of Technology. Satoshi is, in addition to being a colleague, a friend, and we're very privileged to have him travel all the way from Japan to attend this meeting and share his thoughts with you this morning for that. Now, a few little facts about Satoshi. He graduated from the University of Tokyo with a PhD in information sciences, I think, or information technology sciences, I think. And he is a leading advocate for supercomputing in Japan and is involved with many of the initiatives in Japan for supercomputing activities. The system at Tokyo Tech is always on the high part of the top 500 list and the green 500 list. He is very involved with efficient computing, GPU computing, as well as many ranges of supercomputing in the scientific computational sciences. Another aspect of Satoshi is I believe he is the fastest human in high-performance computing. So that means that he averages throughout the year, we just kind of roughly calculated, somewhere around 75 miles an hour every hour throughout the year with his travels. And there are a few people who keep track of this. So not only do you have one of the world's experts on computing and data, but also one of the fastest people on computing and data in many different respects. So it's my pleasure to introduce you to Satoshi and let him talk to us about a variety of different topics. Thank you.
Thank you. Thank you, Bill. Good morning, everyone. Hello. Okay. Thank you, Bill. Yes, it's a pleasure to be here, and it's a beautiful scenery, and I have many friends at NCSA. And as Bill said, I try to practice. I design and build fast supercomputers, and I try to be a very fast human being myself. And so it's such a shame that the speed, the consequence of this is I don't get to spend too much time in a single location. So I'm missing all the nature. And hopefully today's talk will be more worth your time, since by attending my talk, you'll be missing going out and having a trail hike or something. So, so we're in the same boat. So what I'll talk about today is mostly about data, memory, and big data. And the first part of the talk is largely to have to do with memory hierarchy. I'll talk more about in-depth big data and how we believe it's going to converge with high-performance computing in a very pragmatic way. And then at the very last part of my talk, I will claim that this convergence between big data and, the data and HPC is actually inevitable. It's a technological inevitable occasion. And that's driven by the end of Moore's Law. So with that, I will start my talk. Just a little introduction about my institution and our center. So Tokyo Tech, you can think of us as sort of like Caltech or MIT of Japan. In fact, the number of professors, students, and so forth, actually very similar to MIT. And the difference between MIT and us one thing was we're a national university, we're a public university, but also have a supercomputing center, much like Illinois. So we're one of the national centers. We have our GSIC is one of the national centers in Japan. But actually, we've been a supercomputing center since 1988, when we had our first ETA-10 machine. So if any of you are old enough to remember how wonderful that machine was, yes, we had that machine for 5 years. Anyhow, so we've been fielding this series of supercomputers now. This is on a series, and we are now part of this consortium, just like Exceed, called HPC-AI, but I'll get to that later. So just a very brief history. So Tsubame 1, one of our, the first series of Tsubame, it's got 85 teraflop machine back in 2006. It was the first supercomputer to beat the Earth simulator in Japan. And 2010, we designed and built the Tsubame 2 supercomputer along with other vendors. 2013, there was an upgrade. Now it's about a little less than a 6 petaflop machine. It's heavily accelerated by GPUs. Some achievements. This is a 2011 Gordon Bell Prize winning application. It's a 2 petaflop sustained run on what's called a dendritic solidification, basically metal crystal solidification, and very important for solidifying lightweight metals. Now, 2015, we upgraded all the GPUs to the latest K20X. So compared to we're second fastest supercomputer in Japan, both in terms of top 500, but also with a peak. And in fact, we compare the K computer, which is in Kobe, currently the fastest supercomputer in Japan. We're about, you can argue that in single precision, we're faster than they are. In double, we're about half the speed. And so in terms of the absolute speed, we are somewhat in the same ballpark. Of course, K has more memory and so forth, so we also use K computer. We like it very much. But if you can compare the cost, the K computer, the cost of ownership over 6 years is about $1,400 million, whereas including electricity, which is about 20 megawatts, K is one of the very rare supercomputer where running LIMPAC is not the most power-demanding workload. Can anybody guess what the most power-demanding workload for K is? NAMD. No. It runs NAMD, but no. Actually, it's Stream. No. That's because K has no throttling on the floating point units. So, it uses electricity no matter what. And then when the memory system kicks in, that's the maximum usage. So anyhow, we're about 45 to 50 million over 6 years, so about a factor of 30 different. And a lot of people ask us, so why K and Tsubame are so different in terms of cost? I mean, have I bargained well with all the vendors and so forth? Well, maybe so. But you could also argue that Tsubame is using latest technologies because we're mostly we use more or less commodity components, but the top of the line commodity. And a lot of people mistake the use of commodity processors as being cheap. However, that's not the case. Actually, in IT, as we all know, with devices like this, like your latest iPhone, the latest technology has to actually make it to the consumer space first. So I got my high definition screen on my 5-inch iPhone, and no other device does that. So things like silicon photonics, things like use of many core, things like using fast memory, and the use of, and also Tsubame was one of the first supercomputers to use SSDs in all the nodes. So in some sense now it's called burst buffers, but we had this back in 2010 to accelerate the I/O already. Now, so this is Tsubame now, and just to show you a few other applications, because this is also important for the future, for the later part of the talk. This is a lattice Boltzmann application, but extended to be able to handle turbulent flows. And this runs on 4,000 GPUs of Tsubame for about 0.6 petaflops. Now it's about now it runs at around 1.2 petaflops on a new GPU. So basically, we had virtualized the entire Tokyo, the map, about 10 kilometer by 10 kilometer area. If you've ever been to Tokyo, the center, right in the middle, the green part, that's the Imperial Palace. And then you have this circling train line called the Yamanote line. So basically, we were simulating everything inside. And so we got the buildings, we got the topographic map and everything. And we can simulate the entire wind flow within the city of Tokyo. So this looks the wind flow looks very smooth, but actually Tokyo has lots of skyscrapers, much like Chicago. And when you have a whole bunch of skyscrapers, and when you have wind, then that actually causes tremendous turbulent flow, and that causes things like what's called heat island phenomena, in which you get concentration of heat because it blocks the wind from the bay, and thus elevates the temperature of the city, which elevates the electricity usage and so forth. So that's sort of a simulation we run computationally. And for Tsubame, we're right now working on our new machine, which will just be commissioned 2016. And there are various facets of the machine, including greenness, including being able to very wide spread usage, because an academic supercomputer, we'll be bringing in lots of cloud technologies. We'll be bringing in various technologies to make the machine very transparent and visible. But we also have a very heavy emphasis on the data aspect, well, the big data, but also to deal with things associated with data like deep memory hierarchy. So here are some of the target numbers. The machine will be somewhere around the 20 petaflop range, but very high memory bandwidth, very high network bandwidth, but also very high capacity, high bandwidth in the memory both the memory and also with the I/O subsystem, including use of non-volatile memory in order to accelerate I/O. So if the cost meets right, hopefully we'll have petabytes of flash, and then be able to drive the I/O subsystem at over terabytes, several terabytes per second. Just before I go to the main part of the talk, since Bill wanted me to introduce you to a little bit about the status of the Japanese HPC, I'll talk a little bit about the status quo. So we have a consortium called HPC-AI, which is very much like Exceed. So technically there are about 65 supercomputer centers in Japan. But the major ones that are mostly run by universities, just like the NSF centers here in the US, there are 9 of them, plus the K-computer, and plus a few others like the Earth Simulator. So these are connected, and there's some agreement in doing a single sign-on, and also having a shared common storage I will allude to later. So currently, and that's all connected by our current national backbone, which is SINET 4. And so the aggregate performance of the entire infrastructure is 25 petaflops as we speak. However, and I think it's gone up to about 40 now. And we are planning for, Japan is planning for having the future post-K machine. So currently, like I said, the K is the fastest supercomputer. By 2019, and officially commissioned by 2020, there will be the post-K supercomputer. The project's been approved. The only thing that we're not quite sure of is how big the machine will be, because we're not quite sure how much money will be spent. But it will become the fastest machine in Japan in 2019, 2020 timeframe. And I can't tell you the technologies or the details or how fast it will be, but you can but it's pretty much set that it will be at least several hundred petaflops. Probably a little faster than, very likely faster than or the other Coral machines, a little bigger machine than that. But also we will have intermediate machines in 2016 to 18 timeframe, which are like the Tsubame 3 and what's called a post-T2K supercomputer. These are machines that are going to be fielded by folks at University of Tokyo. Just give you let me get my pointer. Right, this is much better. So this is post-K, and these are the post-T2K. So in fact, all the centers have been asked to provide a roadmap for the coming next 10 years. So all the centers all the way from north of Hokkaido to Kyushu, we have various plans. And the plan says that and also the current status says we have about, right now, spring of 2015, some new machines been commissioned, so we should be about 40 petaflops now for the total within the nation, including K. And by 2021-22, if you believe in all the plans by the centers, if you add the post-T2K, I'm sorry, the post-K, and all the centers, the plan of all the centers around that time frame, we should be about an exaflop in 2021-22. So we probably will not have an exaflop machine per se in 2021 timeframe, but we will certainly, the total capacity, the aggregated capacity of all the supercomputers, the major academic supercomputers in Japan should be about an exaflop if things go well. So that's the context, but what are the problems? So I showed you some applications here, like the ones, the Gordon-Bell application, then there were, the city simulation, and there are, of course, lots and lots of simulations running on the Tsubame, lots of simulations running on the K computer and other machines. So as we were planning for the post-K machine and other machines, so we were running various workshops, we're running panels and so forth, just as you do here in the US. We were looking at various classes of applications running on our major machines. And we got a lot of statistics, but one important statistics is what's the memory usage of these machines. To be more specific, what's the required memory capacity versus the memory bandwidth? So you can take a plot on the graph here on the right-hand side. This is a graph that says, given an application, how much memory will it require if you go out, extend all the way to exascale? And then what will be the required memory bandwidth if you're going to achieve reasonable efficiency on these machines so that time to solution will be reasonable. So it turns out that, of course, the plot is all over this, but it turns out that most of the applications require both high memory capacity and high memory bandwidth. And this is a challenge because then we looked at what kind of machine we can build. And it turns out that most of the machines will not be able to fit this category where we had the highest density in terms of the applications that are occupying this space. So there are several classes of machines we considered, but even the machine we thought, given the power and cost requirements, limitations in fact, that even the machine we considered that would be general purpose, representative of a general purpose machine in 2020, will be the memory capacity or the bandwidth will not be enough. Whereas if you try to build a machine that will satisfy the application requirements in this space, we will not be able to meet the power budget or the cost budget required. So that's a big problem because as we go forward, we'll be faced with not so much the flops. The problem will be mostly in memory. So, of course, there are lots of new technologies, upcoming technologies. There are 3D, there's 3D integration of the memory, and then the future processors like the Xeon Phi or the NVIDIA Pascal or the Fujitsu Spark FX11. They're using all the 2.5D stacked memory technologies. So it's coming. However, although these types of machines will allow you to have fast memory, but these of up to about maybe like over a terabyte bandwidth in some instances, the capacity of these memory will be limited to something like 16 gigabytes, 32 gigabytes, and so forth. And such will only go to prove that this capacity versus the memory bandwidth requirements will not be fulfilled. So what do we do? And very similar for the DOE exascale target. So what do we do? Well, there's a batch of non-volatile memory technologies that are appearing on the horizon. And many of these promise high, not only non-volatileness, but because of non-volatileness, you can it can actually facilitate large capacity. But the consequence, again, of this is that although you may be, unless you believe in storage by HP, the capacity of these will be large, but it may even be slower than DRAM, than conventional DRAM, for the most part. So in the essence, what we'll have is very much likely to have is a system where you have extremely deep memory hierarchy, fast memory to slow memory, and the hierarchy will be much deeper because there will be there'll be differentiations of DRAM hierarchy, and also there will be some additional novel memory hierarchies inserted either at the cache level or below the DRAM in order to accommodate more capacity. So again, some of us realize this is a story. But then the problem is what's the algorithm? Or how do you program this thing? So given the memory hierarchy, the very deep memory hierarchy, can you have algorithms that can deal with the architectural change? And even if there are algorithms that can deal with this algorithm change, can you actually program them at ease? Can you actually program them, effectively program them without having to muck around the source code and basically change the entire contents and have this really, really enormous code which doesn't really resemble the original algorithm at all. So thus, one work we're doing is to try to not only work on a class of algorithms that are communication reducing, so reduce the communication at the vertical hierarchy of the memory stack, but also we will try to make it easy for people to program this. So one thing we're doing is to work on some CFD problems, like the ones I showed you that demonstrated on Tsubame. So for example, the city simulation you saw runs at about a petaflop like I said, runs at about a petaflop on Tsubame. The only problem is that it's not so much the speed, the computational efficiency of the machine that's compromising that we go further out into bigger problem size, but it's really the memory. And basically, the emulating at that scale, this is about 1 meter resolution scale, simulation over 10 kilometer, or 10,000 by 10,000 by 5,000, or about 50 billion degrees of freedom. But beyond this, we'll be running out of fast memory on the GPUs, and thus we will not, this performance will plummet. So the question is, can we actually extend this to the larger CPU memory on Tsubame? Every Tsubame node has over 50 gigabytes of memory instead of 6 gigabytes on a GPU. So can we actually extend this? But even if we extend this, can we retain the performance? And even if we retain the performance, can we program them easily? So that's one of the problems we're trying to solve. So if you have a GPU machine, well, actually Tsubame has 3 GPUs per node and 2 CPU sockets, so it's a 5-socket node. But if you just simplify the picture into just 1 CPU and 1 GPU, then you have a memory hierarchy like this. You have your GPU, you have your L2 cache, you have the GPU device memory, which is 6 gigabytes per second, and at least catalog spec, you get 250 gigabytes per second. Here is a very fast memory. Once you go down to host memory, it's only like about 30 gigabytes per second. And the PCIe, the biggest bottleneck is the PCIe, which connects the GPU to CPU, and it's only 8 gigabytes per second on Tsubame. Now you may be able to argue that this will get faster on the future generation machines, but nonetheless, it'll be a lot slower. If you take a look at the future generation Xeon Phi, or if you look at the core machines, the IBM NVIDIA core machines, the memory here will be something like 500 gigabytes per second or greater, or up to a terabyte, but the main memory bandwidth is 1/10 of that. And if you try to extend that to non-volatile memory, it'll be much slower, even slower. So again, you'll be looking at something like factor 10 to maybe like factor 30 difference between the fast device memory and the large capacity memory. So in order to solve the performance issues, we try to implement the classes of communication reducing algorithms, and in particular for any of these stencil codes like direct solvers or lattice Boltzmann solvers, we can actually have effectively implement this using what are called the temperate blocking techniques. And so on the you can see that on Tsubame, any sort, this is a very any application, any stencil application running on Tsubame will have a characteristic like this. So up to the device memory, it'll run very fast, very, very fast. But once we surpass the device memory, we get about a factor of 30 hit in terms of the performance, and that's because of the PCI Express bandwidth limitation. So we'll try to solve this. But the other is we got applications that are tens of thousands of lines of code. And it's very hard to expect that you would, you tell the application programmer, well, you get great results by doing temporal blocking. Well, the only problem is when you have factor 10 or factor 30 difference in terms of the memory speed, when you try to apply any temporal blocking algorithms and their optimizations, it blows the code so significantly. The inner loop becomes just impossible to manage. That's because you have to not only have to unroll the loops, but also you have to manage all the data movement by yourself. And this data management of this data movement is very intricate, such that if you leave it up to the programmer, it'll just blow his code like crazy. So we'll try to address this by using in various ways. One thing we're doing is try to use compiler techniques. So there's a separate work on this being done by one of our collaborators. But today I'll focus on our runtime solution, which is called HHRT. So just to give you a little overview of temporal blocking. So basically, you divide the domain into subdomains, and instead of and typically when you have a temporal when you do temporal advances, you do one time step. So you compute the inner region, and then you compute the hollow region, and you exchange the hollow region. Well, temporal blocking is basically given the observation of the dependencies of stencil computation, data dependencies of stencil computations, that you can actually advance the inner region by k time steps instead of one, and then have a hollow region of thickness k, and then you do all at once exchange of the k hollow region. So this sort of forms something like the very naive version of temporal blocking. If you look at the data dependency, it forms something like this with the temporal dependency of the data points illustrated here as a triangle. So there are several known optimizations for temporal blocking, because if you do this naively, there will be lots of redundant computation. And some of the proposed optimizations are you restructure the loop structure and you eliminate redundant computations in a very intelligent way. That's good. But then, like I said, that results in lots of code bloat, and predominantly not so much because you have extended the temporal loop, but because you have to manage all the data movement. So what we did was to say, well, maybe this loop thing, extending the loop, that's something that the programmer may have to do. But how can we manage the data movement? And it becomes more complex because it's not just the hollow region management between in the memory hierarchy, but you also have to basically have, most applications are MPI enabled. We have very strong belief that MPI will not die for many years, much to the pleasure of Bill Groff. That we have to also support somehow MPI communication associated with this optimization. So what we're doing is to basically, instead of having the programmers express the data movement, what we do on GPUs, or of course the same technique is applicable to Xeon Phi, processors like Xeon Phi, is to basically virtualize the computation. so that we oversubscribe the many-core processor with more MPI ranks than necessary. And then we'll have them occupy certain numbers up to the device memory. And then instead of programmers manually handling the data swap, the runtime will automatically swap the data. And because of the inherent data dependency, this happens automatically to the extent that the user will only have to describe the temporal blocking and the temporal loop, but all the data management, computation going, data being loaded back and forth will be managed automatically by the runtime. So that's a core idea. So in a normal temporal blocking optimization, you have the original code, you have the computation, you first copy the grid over from the host to the device, or in Xeon Phi, and in offload mode, you do the same thing. And then in temporal loop, we'll loop over computation of the grid points, and then it will then communicate the boundaries, the halo region, to other processors. And then you copy the grid from the device to the host. So the normal hand-coded temporal blocking will expand this loop to a double loop where you loop over subdomains, you copy the domain to host the device because you don't have enough memory, and then you have an intertemporal loop that goes k times instead of once. And then you copy the subdomain into device to host, and then you communicate the halo region and loop over the subdomain. The complexity is in managing this copying of the subdomain to host the device, and this gets complicated because you have to change the code. So, but automating this process, all the programmer has to do is just looks very much like the original program. The only difference is that he will have to basically, the only thing he will have to do is to make the outer loop, to divide up the inner loop into two loops, and move the MPI communication from the inner loop to this somewhere in between the inner loop and outer loop. And it's hard to, without coding examples, this may be a little hard to grasp, but in reality, this change is very, very simple. All you have to do is to take the inner loop. You think, okay, instead of doing one temporal loop, you do, okay, I'll do k steps. So I just add the external loop, and then you adjust the loop count based on the fact that you do k outer loops, and then you move the MPI communication to the outer loop. And this, again, this is very, very trivial. All my undergraduates can do this. So given this city simulation that we originally had, this is about 15,000 lines of code. So it's not a huge code, but nonetheless, it's significant. So in order to add, using this runtime, all we had to do was modify about 150 lines of code. So it's like 1%. And then there are several optimizations that you do. For example, so to the HHRT, without going into details, the HHRT runtime has various ways to allow you to limit the movement of data, so the swapping of the device to the host memory becomes more efficient. And we also had to add some additional optimization, again, without going into details, to make the MPI communication a little bit more efficient, because the original code was communicating over 3 dimensions, x, y, and z, once separately. But the way the thing works, it was much better to do sort of like a scatter-gather type of communication over the 27 dimensions of the lattice-Boltzmann computation. So you do 27, just do 27 MPI iSends, and then you do the receives, the corresponding receives. And actually, it turns out to be a lot faster. So the optimization may look a little like 1,000 lines, but actually it's a very systematic change in the MPI communication. So what's the result? So on a single processor, this allows us to speed up from basically the performance going nowhere and even going below the CPU performance. So this red line was the original. With the minor, and this orange line was the CPU performance. With the with the application of the runtime, this sped up, so it'll be, of course, much faster than CPU. And with this added optimization, it's sped up to like factor 15. So it does slow down a little bit as we grow the problem size all the way to like device CPU memory, but that's because we lose the degree of temporal blocking as we do when we move to larger compute size. So with a moderate compute size, several times bigger than GPU memory, with very minor code change and assistance of the runtime, we're able to speed up the application to factor 15, and largely preserve the performance that you have seen in the code that was only working within device memory. And good news is, well, will this work beyond single node? Can we scale to hundreds of nodes? And so far, all our tests have shown that we can actually do that without much performance loss. So we can handle problems that are 3 times bigger than device memory over many nodes. And to the extent we tested, we only suffer about 13% performance loss. And there's really no suffrage from all the swapping and interaction with MPI. So we are trying to extend this work by automating the parameter tuning. In order to do that, we need a performance model, and we have a performance model. It's more equation-based, but this is just how everything works. So all the data swaps and the temporal blocking and the latency hiding is working. And the good news is the performance model matches the overall execution time, and thus allow us to detect when the parameters in the temporal blocking space is minimum. So this is still work in progress, but we have applied this to the city simulation. We have applied this to dendrite simulation, and we're applying this to other types of stencil codes, and we're getting very promising results. The code changes have been very few, and then the performance gains, even with going past the device memory capacity, has been the performance loss has been minimal. So these and other efforts are very important to handle memory hierarchy. So the second part is to say, what about big data? People may say that's not big data, that's more like deep memory hierarchy. So yesterday's talk there were several talks yesterday regarding big data, including one by a director. And we completely agree in his viewpoint that big data, that tsunami of big data is coming. So in the past, big data has mostly been something synonymous to mining people's privacy to make money. And in a more technical sense, most of the work benefits have been alluded to statistical classifiers using various methods. But big data we believe, is more than that. We believe that there are breaking down of silos, and this is Intel VP Rajiv Hazar has expressed this, with that we have much more data sources that are abundant that we have to process. And also, Thomas Schultes, I think there's a very interesting observation. Our good friend Thomas Schultes, it says the big data is sort of like an inverse problem. So we have lots of data, and then we basically try to induce the problem rather than going from the traditional analytics, where we have the first principle model and then we go forward. So it's like solving an inverse problem. And we all know the inverse problem requires much more computation than forward problems. So computation is not dead in big data. And irrespective, our computational capabilities required to handle massive amounts of data, and the complex because of the capacity requirements and because of the inducing of the problem, not just classifiers, but inducing of the model requires tremendous boost in both our data handling and computational capacities. So that's why we have a whole bunch of applications like graphs and genomics and social simulations and data simulations like climate and observational data. These will require not just cloud infrastructures with some capacity, but tremendous compute capabilities, tremendous bandwidth, And that's only afforded by supercomputers. So if somebody asks me, well, what the future cloud look like? The future cloud will very much look like supercomputers. For at least the core part that's handling big data, because that's a necessity. They won't be able to handle, or otherwise they'll be sorely inefficient. Just a few examples of big data problems, the genomics, but I won't go into details because I think there are a lot of good examples given by yesterday's talks. So we'll have lots of unknown genes and metagenomics data type of example. We have a whole bunch of genomes that can be scavenged from various environments, and we try to sequence everything. For example, the gene in your mouth, you have your human genes, you have all the microbes, you have genes over the microbes, but what you try to do is to sequence everything, and then you try to determine the overall ecosystem of the genes, not just a single organism. So that's metagenomics. And you can do very effective analysis to determine anything from why you have a bad breath to what kind of oral disease you might be susceptible to. But this is very, very compute intensive, not only data intensive, but very compute intensive. So this is a simulation done on the K computer. Very similar code runs on Tsubame as well, about half the speed of K. The problem is that are twofold. One is in the original K computer, because of the way the code was written first to stage the data, it took more than 24 hours to stage the data. So basically, that killed the job. So obviously, K computer was not equipped to handle big data workload of at least the way it was written. The second problem was very compute intensive. So basically, this analysis of oral hygiene required the usage of about 600,000 cores on the K. So, and this is and took several hours. And this is just for a single human being. So if you have lots of human beings, obviously, because you want to sample many of them, this becomes an enormously computationally heavy problem as well. And there are many other instances like social graphs, and that was mentioned yesterday. I think there was one on talk of the graphs. The neural network is about 100 trillion edges. The social networks, again, involving billions of edges, of vertices, and trillion, and is growing to tens to hundreds of billions and growing to trillion edges. So we'll have very awesomely large graphs. Now, the benchmark for determining how fast a given supercomputer can execute a graph problem is a graph 500, and it's a single number benchmark, so there could be lots of criticism to it, but nonetheless, it's sort of an effective benchmark for assessing the capabilities. So what it does is it takes the self-similarity graph or the Kronecker graph that's typically seen in social networks, and then you try to do the breadth-first BSP or the breadth-first search on the generated graph. Then the assessment back in 2010 when this benchmark was created was that because there was a proliferation of the graph processing in the cloud space, even the inventor, our good friend Rich Murphy, who's now at Micron, they had speculated that the cloud infrastructures will certainly be up there in terms of the rankings. And it turns out that but when the rankings are announced and has evolved over the years, there are no cloud infrastructures up on the tops of the Graph 500. In fact, the machines you see on the top are the familiar ones like Sequoia and K and so forth. So you come to wonder why that's so. So for one thing, we all know that these machines now are pretty big, and they may be actually matching, that are smaller in terms of physical size, but because of the efficiency, their density, the number of cores, for example, on Tianhe 2 is 3 million cores. And that's a pretty big machine, even compared to the largest cloud data centers. And also, if you look at the interconnect, and I think this was partly in Scott's dinner talk yesterday, that if you look at the interconnect, the cloud infrastructures are extremely poor because they're largely designed to handle internet workloads, which whose bandwidth is largely governed by the incoming, by the incoming traffic here. So the incoming bandwidth from the internet, it governs the requirement of the overall horizontal traffic within the data center. And when your incoming traffic is only like matters of 100 gigabits, at most what you need is a terabit, and that's why you have this consolidation with the top-of-rack switches and so forth. Whereas for supercomputers, we can't do that. If we consolidate our network, we're going to be pretty much dead. So we have this something like full bisection bandwidth networks, or we have dragonfly networks that also can be full bisection or have very efficient multidimensional torus like the K computer or the BlueGene Q. So if you compare the overall aggregate bandwidth, or even like a machine like Tsumame versus a larger data center, we're 2 to 3 orders of magnitude difference in terms of the bandwidth. In fact, if you look at something like 200 terabits, which is the capacity of Tsumame network, the global internet, circa 2014, is about 200 terabits. And Cisco, and this is the data of Cisco, and also Cisco predicts that the global intra-IDC bandwidth will be about, circa 2016, will be about 2 petabits per second. So 2 petabits per second, the next generation Tsumame we expect to be anywhere from 1 to 2 petabits. So a single machine in a 20 petaflop range actually matches the entire data center traffic of standard commodity data centers that Google and Amazon's and everybody has. So is the inner data center traffic important? Well, if you look at the Graph 500 challenge we're doing, and we're always competing with the Livermore people. So we have our team at Tokyo Tech and also University of Kyushu, along with K people and Fujitsu. We're battling the Livermore and IBM team, and we're kind of neck to neck every time. But if you look at our overall statistics of the efficiency of the occupancy, where the time goes when we run our biggest Graph 500 run, most of the time is spent on network communication. So about 73% on our Graph 500 run, about 73% of the total execution time is in the networks. So this is with machine that has one of the fastest network in the world, and still 73%. So if we ran this on a cloud whose network is 3 orders of magnitude slower, obviously this execution time will blow up by a factor of 3 orders of magnitude. So we're going to be basically nowhere. So that's why we believe that one reason we believe that there should be inevitable convergence of the IDC technology, which are actually pretty good in terms of software malleability, being able to very easy deployment of software, lots and lots of very rich but capable big data software stack, however, being somewhat slow, versus what we have in the supercomputer space, which is very efficient. So the question is, how do you merge these technologies? So the question is, given a top-class supercomputer with all the network and other efficiencies, how can we accelerate the big data software stack? Or how do you formulate the algorithms in the software stack and also the architecture eventually to really boost the big data capabilities of our future generation machines without the data center becoming 1,000 times bigger, which is already too big now. So that's our project, Extreme Big Data, and we are going to apply some of the technologies we're developing here to our future generation machines. So what we'll have will be a programming layer at the top, and then we will have a whole bunch of layers of algorithms layers, system software layers, and so forth. So we'll try to give the abstractions to the programmers that are very familiar looking in terms of the big data software stack, but underneath we'll change everything to be more compliant to use the efficiency of our underlying supercomputing architecture. And so some of the results we have, we're currently number 2 on the Graph 500. Next time we'll beat IBM. The last time we beat them in June. In November we got beaten again. So coming June, one of my students is working very hard with the Fujitsu people to try to surpass Lugin's score. So we'll see how it goes. Greenness on the Graph 500, we got number 1 in 2013. But we're all building a whole bunch of software stack. And because lack of time, I have to skip over most of these, but things like graph libraries that are very efficient. Just skim over some of the technologies. If you're interested, you can read my slides later. We're trying to accelerate MapReduce to supercomputing speeds with the MapReduce implementation that are more or less based on C++ rather than things like Java or Scala, and then use MPI underneath to communicate in order to accelerate MapReduce, and also do automated shuffling of data underneath, and we get tremendous speed up over conventional MapReduce. We'll try to accelerate sorting because sorting is inherent in many of the big data workloads, and we get very good results on this. Unfortunately, with sorting, the bottleneck is in PCIe, but we have a predictive model where it says that the future generations of machines with very fast PCIe or something like NVLink, which greatly accelerates PCIe, we can actually recover most of the performance, so we get tremendous boost over sorting on CPUs. And we're also trying to harness the memory hierarchy in the graph algorithm by putting most of the graphs in non-volatile memory. And just like the example of the stencil computation we showed you, we can accelerate these graph applications even though much of the graph is in non-volatile memory. In fact, for BSP, the same algorithms at top 500, we can put a graph that's 4 times bigger in non-volatile memory than the available DRAM capacity, but we only suffer the performance loss of about 7%. So, much bigger graphs than DRAM, but virtually no performance loss. And all these slides go to explain the algorithm, but I have to skip because I want to get to the last part. And also, we're starting to work on how to accelerate deep learning because that's very important. We think we have some good algorithms that could get. We're thinking we can beat Google and the Baidu guys, but I can't tell you because this is it's a working secret. All right. So we want to get to the last part of my talk, and I'll end this in 5 minutes. So I think we demonstrated that there's inevitability because of the requirements that we need to accelerate big data applications, and big data applications will be much more diverse than present day. And then because of the capacity requirements in terms of performance, we need to have much more efficient underlying architecture like supercomputers. So we need to harness the power, but in order to do that, we have to basically come up with new algorithms and come up with new software stack, especially to exploit the deep memory hierarchy, like I explained to you earlier. So that's good. So, but still people can argue, well, that's about data. And so if you're compute-centric, you may not care. There's a little bit with memory hierarchy. I have my CFD code, I have my molecular dynamics code, I have all these codes, and these are all compute, classic compute. So I'm not going to worry about data, big data. However, the claim here at the last part of the talk is even those, there's inevitability that it'll be more data-driven. And that's because the Moore's law is ending. So we all know what Moore's law is, and we all know what's ending, because we can't shrink the lithography anymore. So then the Nernst scaling is ending, and this is all due to device physics. So the question is, how do we sustain the growth beyond Moore's law? Because Moore's law basically allowed us to make phase changes in our daily lives. Even the existence of internet, the existence of personal computers, devices like this, IoT, and of course the existence of our supercomputers and the growth thereof, and the qualitative changes brought on by the supercomputers applications, these are all basically due to the Moore's law, because we have machines that are 1 million times or even 1 billion times faster than we had 30 years ago. 30 years ago, and even in consumer space, Now, 20, 30 years ago, this was science fiction. But we have this. So that's due to Moore's law. But if Moore's law ends, we won't have progress like this. Our next generation progress cannot be driven, and thus, we'll be kind of stuck in a much more stagnant culture. So, if you think, Blue Waters will be commissioned until, as far as I understand, until 2018, right? And people are clamoring, we need faster machines and so forth. But if the machine doesn't get faster, then what's your motivation for replacing a machine? And so what would the vendors do? If you're going to stick around, if the machine doesn't get faster, you may keep your machine for 15 years, as long as it doesn't break down. So what will the vendors do? There will be no incentive to develop new machines. And they'll go bankrupt. So it's a serious problem. So I'll skip over most of the fabs and everything. Now all the reasons why we're slowing down. The number of fabs is small, transistor counts. So the observation is that when the lithography shrinking ends, the power per transistor basically becomes constant, and it's starting to become constant now. So it'll be we'd be power restricted. No matter what we do, our compute will be limited by the number of transistors we can afford given certain power. But since transistor power will be constant, the number of transistors we can afford per computation will become constant. But we can have more transistors. Certainly, we can build bigger machines. We can lay out silicon. So we can have more transistors, but we can't turn them on at the same time. That'll be the problem. So if we have economics, we can lay out more transistors for the computation. The only problem is we can't turn them on for compute at the same time. So what will happen is that, so a lot of people predict that we have specialization. So there will be customized circuitries or customized processing units per each type of data. So that's because we can have more transistors. But depending on what kind of data, what type of compute we have, we'll turn these on separately, at various timings. And this is already happening in something like this. We turn on the video encoder units, decoder units when we need it. And these are specialized type of data. The processor here in my cell phone, my smartphone, there are accelerator units for video. Okay, so it's pertinent to certain types of data, which is video. Now, the memory will be subject to continued capacity growth with 3D stacking. And especially with the future generation, there'll be some innovations in direct silicon stacking and lower power NVM like our ERAM. And data movement, we all worry about data movement, but actually when we have integrated silicon 3D, what will happen is this will be kept constant, and with the next generation optics that can go up to like terabits per wire, the entire energy bill will be capped, because the reason we need so much energy, and there will be associated latency in the current chips is laid out in 2D. But when laid out in 3D, you can go vertically. So with the proper design, processor design, moving between layers of 3D stack will actually become very small if we go to 3D, direct silicon 3D. And when we have optics, optics, there's a certain cost to launch into the photonics domain. But once you do that, the movement of data will be constant, no matter what distance you go, up to a certain distance. So there'll be some elevation in terms of the energy. But once you do that, no matter how big you make a machine, the energy bill will be constant. And you can drive up the bandwidth by using technologies that come from long-haul carrier. And so this means that data will be free, but compute will be expensive. And this is completely opposite to what we're thinking about towards exascale, right? In exascale, we're saying compute will be free, data will be expensive. But this phase change will happen because Moore's law will end about 2025, 2030 timeframe. So that's where, being an academician. So my concern is what do we do with this clear trajectory coming in the next 10, 15 years, when I hope I will not be retiring and active. And at least students I teach will be living in that realm. So we need to accelerate algorithms based on data properties. And the growth of the data constants that are relevant to data, like capacity or the bandwidth, will be a driving force. That'll be the new Moore's law, basically. And there are several advanced work in the area. I'm not just saying this for the sake of argument. For example, our partners at AIST, which is our government lab, is looking at ultra-large data machines using future generation data stacking, using volatile memory, high-performance logic, optical network, and new architectures. They got lots of technologies regarding voltage-controlled DRAMs. I'm sorry, non-volatile RAMs. So zero usage, zero current. The phase change in memory just driven by voltage. So it'll be almost like zero energy, however, changing the state of the memory. Various types of 3D direct silicon stacking, even using different types of devices. Our friends at some people at Hitachi, they're looking at a new paper at ISSCC this year. They have announced a CMOS-based Isling combinatorial optimization problem. So this was in the realm of superconducting quantum annealing chips, but now this is using a more classical Isling model in spintronics, but they have emulated this in CMOS, so they can run this at room temperature. Of course, technically there are some differences between this and quantum annealing because this is room temperature, so you can't have multiple states. Rather, you have to have a random number generator. But still, they say the single chip that's been fabricated is about 2,000 times energy efficient than doing these types of optimization than CPUs. So you can imagine these types of devices coming to, depending on, embedded into chips for certain types of applications. And then the optics, again, the IST people are working on advanced photonics with single light source, multi-wavelength technologies with optical waveguide chips with the optical 32 by 32 optical switches. And because one of the problems with having optics in the multicolored optics in supercomputers or data centers was the fact that the light sources were expensive. When you have multiple colors, you have to have multiple laser diodes. So they're solving the problem by having a light well, basically a single light source, and then they distribute the light source using fiber. So you can have a very powerful single source optics, and then at each endpoint you can actually use the distributed light, and thus achieve something like 32 color modulation. And adding other modulation techniques, they hope to be able to achieve within a machine not 1 petabit, as we see in the current photonics, but something like a half a petabit worth of bandwidth capacity. And this will really, really speed up the bandwidth intensive applications. So, and there are many other things like how to deal with resilience. My personal belief is that all this software stuff is a hoax, but I won't go into that. I'll be writing a paper on it. And then we're building some prototypes. And there are similar efforts like the machine sort of has a similar concept. And, but with these kinds of technologies, even in 2022, we think we can build machines, put the entire K computer into a single rack, and then but have much more higher memory capacity. But of course, it's not the flops that's important. Again, it's how do we drive the algorithms, the ecosystem, using the increase in the data capabilities, the bandwidth and the overall capacity, and how to solve the software problems associated with that kind of growth. So with that, the future looks bright. Hopefully, at least until I retire. But we have to focus on data because it's inevitable, not just because of big data requirements, but that's the only way we can speed up our future generation machines. And if we don't achieve to do that, the Crays or IBMs or the Fujitsus may, I wouldn't say go bankrupt, but they will stop making supercomputers. With that, sorry, I may have gone over time. That's my talk. Thank you.
Thank you very much. We have time for a question or two while we switch there. So, Win Mei.
Satoshi, great talk as always. But, my question is, when I look at your current approach to speed up these analytics, we seem to be rewriting the application in C++ and probably bypass some of the the Hadoop file system kind of things, right? And how sustainable is this, and how scalable is this in terms of covering all these workflows and so on that use heavy Java infrastructure and hierarchical objects and so on?
Yeah, that's a very good question. So the existing software stack uses like Java, Python, and Scala, and so forth. So how do we? Well, there are we're trying to deal with this in various ways. In fact, the graph algorithm, the graph package, the scale graph uses X10 and C++ underneath. X10. So there's real users of X10, by the way, and that's because of our collaborators in IBM. My former student who's now an IBM guy. He is at IBM Watson. So, of course, the very simple way is to try to have interlingual interfaces. So, for example, scale graph, we're currently building a Python interface to it. So you can actually write your code in Python and embed the entire graph architecture into the Python ecosystem. So that's one way. So that's a very simple way. The bigger question is how can we? I think we have to kind of look at the problem from a different angle, as to how to have these. Where do these sources of inefficiency comes from? And that's because they are written in Python, they are written in Java, they are written in Scala, and when so we really have to look at these languages because there are lots of 20 years worth of research accelerating these languages, like better JIT compilers, better analysis, but they have not been applied to practice, or they were applied before, but they've been thrown away in the light of this productivity stigma. And so we have to basically try to resurrect. Not only look at the software stack, how to make it efficient, we may even have to go and look at these underlying technologies to make them go fast. So they're all programming languages, for example. They're all libraries. Why can't they principally be made fast as Fortran, for example? So I think there are a lot of work to be done to accelerate the software stack.
Satoshi, thanks very much for a stimulating update talk on Tsubame 3 as well as the vision for data-centric computing. I think it's clear to many of us what kind of an impact this can have on predictive science in the usual hypothesis-driven sort of realm, where the amount of validation that's required, tremendous amounts of observational data compared against the expanded volume of simulated data is extremely challenging, and I think you gave a clear picture of what that might entail.
Yeah, there's more to it, but yeah.
Yes, but I would like to ask your perception of the other extremely large arena of large data-driven predictive science that involving, for example, machine learning in various application domains. And here you're dealing with huge amounts, multi-petabytes of complicated observational data. How do you deal with the transfer of that data to the various machines and so forth, and then how can a machine handle it? And I'll just mention in passing that I had an interesting discussion here at this meeting of a genomics application that is being targeted for Blue Water's engagement. And so we are talking about moving these large predictive data-driven statistical machine learning approaches to the really large modern systems.
Yeah, so Bill, right on the mark. In fact, that's why, we're trying to work on it. I think lots of other people are starting to really work on this because it's a fundamental problem, and it kind of penetrates throughout the software stack. First is, like you mentioned, how do we move the data in the first place? How to store data, how to access them efficiently. The second is how to process them. What are the underlying software layer to the abstractions to process them? What are the algorithms? One thing I didn't talk about today is even matching observation to computational simulation. There are various techniques that are evolving using more predictive methods in order to make these matching more efficient. And with respect to things like for example, take a look at auto driving or things like drones. So we're working, in various analysis that was done for us by companies that are working on these types of deep learning issues. They expect you need several exaflops of compute just to have a manageable drone which doesn't fall from the sky, or auto driving cars that won't crash in real situations, not like Google cars. By the way, Google cars are known to crash as well, but they've been hiding away this. Apparently they're hiding away this. But in a real traffic situation, we were working with an auto company, and they say it's a very complex problem because for example, any large company will be selling cars everywhere in the world, and people in the world are dressed differently, and the environment's all different, right? It's green here, but in deserts it's all brown, or in the cities it's all buildings. So they have to amass tons of petabytes of data, at least, in order to arrive at a decent classifier. But there's a problem that these deep learning classifiers are extremely hard to accelerate because that's currently fundamental to the algorithm, limitations in the algorithm. So there are all these problems, and I don't think I have a straight answer to this, but it's a huge challenge that I think this community ought to be working on, not just simulation. So we still work on simulation science, but it's exactly sort of problem that are arising that I believe require help. So, all this effort are not because we think that big data is a fad, or that supercomputing, we have a fear of supercomputing being overcome by the big data requirements. I think it's fundamental that supercomputing be involved in big data per se, because of the requirements that are being induced by the problems, exactly some of the problems you mentioned. But this is all the way from the application algorithms all the way down to the systems. Yeah.
So, Satoshi, thank you very much for a great discussion and giving us a lot of things to look at in slides that we'll go back to. So thank you.